Adaptation laws for parameter update. Substituting 32 for UT into U macron T, and rearranging yields. Where T equals GCOSX1D, theta equals 1 liter minus 1 liter caret, and in which gamma E is constant gain value. Rearranging yields. Then, the adaptation law is designed as. Hence, the final error system utilized, 37, results in. The following is assumed to define the upper and lower bounds of each unknown parameters. Where theta is the estimated constant parameters, theta underscore, theta macron are unknown lower and upper bounds of the estimated parameters as shown in system parameters, respectively, which will be set to the amount of percentage of their true values. Theta t, vector is designed to update using a projection-based algorithm as. Where project, is the projection operator and each parameter is adaptively updated using adaptation laws for online estimation of unknown parameter as follows. It is straightforward to make a conclusion that the above adaptive control approach is applied to 36, and then the parenthesis term in 36 will be going to 0, resulting in 38, if both are perfectly cancelled, which yields globally stable tracking result. Numerical results. The initial condition of inverted pendulum angles is given as x10 equals, rad, deg, as shown in where each actual angle of the pendulum track the desired angle x1d equals 0, starting from its initial value. Note that the initial angular rate, x20, is 0. N, the actual angular rate tracks the desired angular rate of the inverted pendulum. N, their tracking angle errors are shown in the top plot and the error rates are shown in the bottom plot, where the errors and error rates are close to 0 and thus the tracking system works well. The control inputs are N, the control input shown in plot, A, is the designed control input N, 32, which is used for the control input of the system dynamic model given N, 15, the control input shown in plot, B, is the control solution given N, 31, of the tracking aerodynamics N, 34, which enables the global stability, and finally the plot N, C, is proposed controller of this research, i.e., the closed-loop adaptive tracking control input designed in 35. Is the estimate of the time-varying parameter, L awful, in which the simulation parameters such as mass, m, length of the pole, L, and inertia of the pole, J, are combined together and the values used in simulation are as follows, m equals 0.127, L equals 0.3, J equals 0.05, and G equals 9.81. The percentage of the upper and lower bounds given in 39 is set to 100%. The nominal value of 1/L is 0.612. Thus, the upper bound is 1.232 and lower bound is 0 as shown in and the time-varying parameter estimate is varying within the bounds. The Aerodynamics E2t, developed in the main body of this lecture are shown in the plot. A, is the second equation of 22, with the control input given in 31, the plot, B, is the output of the aerodynamics given in 34, with the control input 35, and the plot in C, is the final aerodynamics given in 38. In those velocity errors with regard to the dynamics are shown. The reference velocity, error control gain constants, gain value, and control input gain matrix are. Tracking angle, x1t, x1dt. Where I2 is 2 times 2 identity matrix. Tracking angular rate, x2t, x2dt. Angle and angular rate errors, e1t, e2t. Control inputs, a UTN, 32, BU macron TN, 31, and CUTN, 35. Parameter estimate, LT. Aerodynamics of the pendulum, a E2TN, 22, BE2TN, 34, and CE2TN, 35.